Good evening, Professor. This presentation covers the principle of measuring high-frequency electrical network with network analyzer. So today we will going to discuss about vector network analyzer. Vector network analyzer. So what is the vector network analyzer basically? This is the measurement machine which is used to analyze network that allow characterization of linear and non-linear device behavior. Basically, RF fundamental and take you through the concept of reflection, transmission, and S parameter that present will review the major component of a network analyzer as well as advantage and limitation of different hardware components. This presentation will cover the various accuracy enhancement and various calibration technique. Vector network analyzer measurements performed on filters, amplifiers, mixers, and balance components. This mode is not about computer networks. Some people think we are going to talk about routers, bridge, hub, but the network analyzer was coined many years ago. There was no such things as computer networks. Back then, network always referred as electrical network. Today we will going to about network analyzer measurement. We speak mostly about devices and their components. So what type of devices are tested using the network analyzer? There are some examples including passive and active components. There are many devices need to be characterized for both linear and non-linear behavior. It is not possible to completely characterize all these devices with just piece of test equipment. So here you can see some are passive and some are active components of devices which is being used and tested by the VNA. Here we can see passive elements like duplexer, diplexer, filters, couplers, bridge, combiners, adapters, and dielectrics. Basically a RLC, inductor, resistance, capacitance, antennas, multiplexer, RFIC, which is basically our concern for focus about RFIC, MMIC, receivers, tuners, converters, and transistors. Here we can see device task measurement model. Here is a simple to complex responsive tool. In y-axis you can see here, and in x-axis it is from simple to complex. Stimulus type, DC, CW, set frequency, noise, two-tone, multi-tone, complex modulation, pulse RF, and protocol. So there are some modules which is being measured by the VNA. So here we discuss about light wave analog to RF energy, that is high frequency device characterization. There are some incident light and reflected, and some light wave will be transmitted So now we will fully understand the relationship of electromagnetic wave. We must also recognize the term used to describe them. Common network analyzer technology has been incident wave measured with R for references. The reflected wave measured with the A receiver and the transmitted wave is measured with the B. Here we can see reflected wave is described by the A and transmitted with the B receiver. The amplitude and phase information of these waves, we can quantify the reflection and transmission. Some of these common measured terms are scalar in nature. For example, return loss is a scalar measurement. This one. Our impedance results from vector reflection measurement. Some like group delay and purely phase related measurement. Radiation reflection is often shown as A divided by R, or radiation transmission that are often shown as P divided by R, related to the measurement received used to the vector network analyzer. Why do we need to test components? There are so many reasons to test a variety of components. Verify specification of building block for more complex RF system. Ensure directionless transmission of communication signal, that is linear, constant amplitude, linear phase, constant group delay, NonLinear, harmonics, intermodulation, compression, AM to PM conversion. Ensure good matches when absorbing power, that means antenna. For component production, a manufacturer must measure the performance of their product so they can provide accurate specification. This is essential so prospective customer will know how a particular component will behave in their application part. That's why we need to test the components to launch these component or the system into a market or any lab to land transmission. The need for both magnitude and phase. So why we need both magnitude and phase? In Spanish simulations, magnitude only data is sufficient for out needs. Like we may only care about the gain of an amplifier or stop band rejection of a filter. However, as well as explore towards this paper, measurement phase and critical element of a network analysis. This is like complete characterization of a linear network as one and as two parameters necessary to develop circuit module for simulation to design matching circuit, like complex or time domain characterization, vector error correction. Time domain characterization requires magnitude and phase information regarding the time. Transmission line basics. Low frequency wavelength should be higher than with the wire length. The need for efficient transfer of RF power is one of the main reasons behind the use of transmission line. At low frequencies where the wavelength of signal are much larger than the length of circuit conductors, a simple wire is very useful for carrying power. Here we can see in this picture, current travels down to wire easily and voltage and current are the same no matters when we measure along the wire. Critical importance of that allows transmission lines takes on characterization impedance, that is Z0, frequency and wavelength. There is some criteria for the frequency and wavelength in C-pin picture. For the 100 GHz, the wavelength should be 3 mm. For the half frequency wavelength, near about or equal or less than length of transmission medium. Need transmission line of for effective power transmission. Matching or characterized impedance is very important for a low reflection and maximum power transfer. Measured envelope voltage depend on the position along with the line. Smith chart review. So basically the Smith chart review we use to know the impedance of her DUT. All the programmable calculators and computer takes the drudgery out of doing the math. A single number does not always give us a complete picture. In addition, impedance almost certainly changes with frequency. So even if we did all the maths, we could end up with the table of number that may be difficult to interpret. Here we can see a simple graphical method can solve this problem. For positive resistance, the absolute magnitude of for a reflection of T varies from 0, which is a perfect load, to unity full reflection at some angle. So we have a unit circle. Here we can see. The proper solution was first used in 1930 when Philip Smith mapped the impedance plan, creating the chart that bears his name, Smith chart. Since unity at 0 degree can be plotted polar plane and represent infinite impedance, both plus and minus reactance as well as infinite resistance can be plotted by the Smith chart. If you can see plane onto a polar plane. So that is the basic use of Smith chart. Transmission line. Transmission coefficient T is defined as the transmitted voltage divided by the incidence voltage. Here we can see incident and divided by the terminated voltage. Insertion loss can be defined with 20 log V transmitted, V incident is equal to 20 log T, and gain can be defined by dB is decibel, 20 log into V transmission divided by V incident is equal to 20 log tau. The DUT exhibit attenuation or insertion loss. When insertion loss is expressed in dB, a negative sign is added in the definition so that the loss value is expressed as a positive number. In communication system, signals are time varying. They occupy a given bandwidth and are made up of a different magnitude frequency component. Next is linear versus non-linear behavior. Before we explore linear signal distortion, we need to understand linear behavior. Devices that behave linearly only impose magnitude and phase changing on out input signal. Any sinusoid appearing at the input will also appear at the output at the same frequency. Here we can see. This is called a sinusoidal wave with the same frequency with input and output. No new signal are created here. When a signal sinusoid is passed through a linear network, we don't consider amplitude and phase changing as a distortion. However, when a complex time-varying signal is passed through a linear network, the amplitude and phase shift can dramatically distort. Here we can see the time domain waveform. This is a distorted wave. Here we can see in this picture. We are talking about nonlinear behavior. Nonlinear devices can shift input signal in frequency, a mixture, for example, like or create new signal in form of harmonic or intermodulated products. Many components that behave linearly under the most signal conditional. If you want to be that this component participate in a behavior or linear behavior motion, that we need to optimize our data and to exhibit some signal condition that a non-linear behavior can be transferred to a linear behavior of a component. Criteria for distortional loss transmission. So now let's examine how linear network can cause signal distortion. There are three criteria that must be satisfied for linear distortional loss transmission. First, the amplitude of the device or system must be flat over. This should be flat for all at the frequencies. At bandwidth or magnitude. This means all frequency with bandwidth will be attenuated identically. Second, the phase response must be linear over the bandwidth. Here we can see. And the last device exhibit a minimum phase, like a minimum phase, very low distance response, which means at 0 Hz DC there is 0 degree phase shift. There is no such a phase shift at a 0 degree or 0 plus minus 180 degree. It's okay, we don't mind at a inverted signal. How can magnitude and phase distortion occur? So this occur due to the phase shifting at different degrees. So this is about the distortional loss transmission. This is all about VNA and its application in different active and passive component of a devices and electrical circuits. So that's all about VNA and its application part. Thank you.